Hey, welcome back to your favorite Calculus 2 class. We're going to take a look at parametric equations in this section. And so we're going to study new ways to define curves in the plane. So instead of thinking of a curve as the graph of a function or equation, we can think of it as the path of a moving particle whose position is changing over time. So if you notice in this down below here, this fails the vertical line test, right? So this is not a function. However, the nice thing is with equations, with parametric equations, we can use these to describe more general curves than those described by a single function, and that's because we can find the orientation of the curve will help us to trace out a path based on time t. Okay, so let's look at the definition of a plane curve. So we're going to have x and y defined in terms of a third variable t, and that will give us our set of parametric equations like you see down below in example 1 here. And the orientation of the curve, I'll show you how we'll kind of sketch that out and show you the direction or the orientation of the curve based on our t here. And we'll start with what's called an initial point, and then we'll go to its terminal point. And finally, when we give parametric equations and a parameter interval for a curve, we say that we have parametrized the curve. Okay. And the equations and the interval together constitute a parametrization. Just a little bit of vocabulary there. So let's go ahead and sketch. Let's kind of show you what we mean here with a couple of parametric equations. X is t squared minus 4, y is t over 2, and notice that the t is between negative 2 and 3. And so what I'm going to do first is I'm just going to make a table of values. Based on t, and I'm going to start with negative 2. I'll just do the integers here, negative 1, 0, 1, 2, and 3. And then I'll find my x values. So x is t squared minus 4. So I get negative 2 squared minus 4. So I get 0. And then I'll do it for the next t values. Negative 1 squared minus 4. So I get negative 3. I get 0 squared minus 4. I get 1 squared minus 4. I got 2 squared minus 4, and I got 3 squared, which is 9 minus 4, which is 5. Now let's find the y values. Our y is t over 2. Now I'm going to plug in negative 2 first. So I got negative 2 over 2, I got negative 1. And now let's throw in t being negative 1. So I got negative 1 over 2. And then I got 0 over 2. 1 over 2, and I got the 2 over 2, I got 3 over 2. And so my points, let me erase this here. My points x, y will be 0, negative 1. I got negative 3, negative a half. I got negative 4, comma 0 for my x, y. I got negative 3, comma half. 0, comma 1. I got 5, comma 3 halves, and so on, right? And so let's go ahead and sketch these parametric equations. So when t is negative 2, it spit out 0, negative 1. So this is my initial point when t is negative 2. It spits out an x of 0 and a y of negative 1. And then when t is negative 1, I get negative 3, negative a half. When t is 0, I get negative 4, 0. So this is t being negative 1. This is t being 0. T being 1, I get negative 3, and I'm up a half. This is t being 1. When t is 2, I got 0, 1. And finally, when t is 3, I got 5, 3 halves, so 1.5 to there. And so this thing goes in that direction. So I'm going to go ahead and put my arrows on, indicating the direction based on t. This is finally where I end my terminal point at the end. And so the arrows indicate its orientation as t increases from -2 to 3. Now you can actually check this in Desmos. So let me show you how you do that. Let me pull up Desmos graphing calculator. And what you do is you put it in as an ordered pair, t squared minus 4 comma t over 2 was the y value. So x was t squared minus 4, y was t over 2, and then it was from -2 up until a t value of 3. And you can see your parametric, your plane curve there. Okay. So that's how you graph them with the calculator's help, of course, to kind of check your work. Now, it sometimes will happen that you can have different sets of parametric equations that have the same graph. So, for example, this set right here, down below, it's the exact same. It has the same graph as the one we just did. But note, with this one, t is -1, and then it goes up until 3 halves instead of going from -2 up to 3. And so this one is this graph is traced out more rapidly based on time t. Okay, so even though the visual is the same, it's going more quickly. And of course, that's just the note on how we do that in Desmos that I just showed you. Let's do another one here, and you can try this. Not a bad time to have you pause the video and try this one on your own. But I'm going to go ahead and make a table t, x, and y. We're going to go from 0 up to 6. And we got x is sine of pi halves t. And so let's let t be 0. We got sine of pi halves times 0. We got sine of 0, which is 0. Now let's throw in 1 for t. Sine of pi halves times 1. So I got sine of pi halves, which is 1. Let's throw in 2. Sine of pi halves times 2. I got sine of pi, which is 0. Sine of 3 pi halves, -1. Sine of 4 pi halves, 0. Sine of 5 pi halves, 1. Sine of 6 pi over 2, which is sine of 3 pi, 0. Now let's do the y. Notice the y is just t. Y is just t. So if I let t be 0 again to start out, y is just 0. Then I'll let t be 1. Y is just a 1. And so on. And so there's our points, right? I got 0, 0, 1, 1, 0, 2, and so on. I'm going to graph those. My initial point is 0, 0 right here. I'm going to start right there. When t is 0, and then I'm going to go to 1, 1, and then 0, 2, and then -1, 3, 0, 4, 1, 5, 0, 6. And I could put some more points in. You'd see that it's got some curvature to this. Whoops, why did I do that? Let's put the arrows on until it finishes right there, t being 6 at that final point. Again, the direction of the motion is shown by the arrows here, right? Well, we can also do what's called eliminating the parameter, so we can put it into a rectangular equation form. And so what you do, like our first one, we had x equals t squared over -4 and t and y equals t over 2. And so you can solve for one of the variables in terms of t and then just substitute it in, and then you'll be left with x's and y's at the end. And so we'll go ahead and we'll practice doing that. And of course, this is, this is a parabola that opens to the right, as we did in that very first example. So let's go ahead and do another one, and we'll adjust the domain on this one as well. But we'll eliminate the parameter as well. So number one, let's go ahead and solve for t with one of the equations here. We got x equals 1 over the square root of t plus 1. If I square both sides, I got x squared equals 1 squared over square root of t plus 1 is just t plus 1. Multiply both sides by t plus 1 and divide by x squared both sides. I get t plus 1 equals 1 over x squared. Then I subtract 1. So I got 1 over x squared minus 1. Or if you want to get a common denominator, 1 minus x squared all over x squared. And now what we'll do is we'll substitute it into the other one. We got y equals t over t plus 1. So y equals t. Y equals t, which is 1 minus x squared over x squared all over t plus 1. Well, let's get a common denominator. So we got 1 minus x squared over x squared over 1 minus x squared plus x squared all over x squared. Of course, those are gone. Then I'm going to multiply by x squared over 1 here. And notice these x squareds are gone, so I just am left with y equals 1 minus x squared. Bring it up here. In other words, we've got this parabola flipped over, right? Reflection about the x-axis and bumped up 1, right? We know, so it's flipped over and bumped up 1. Now, I've got a different domain. Notice my t here has to be greater than -1. And so we're just going to have to adjust our domain on that. So let's go down here. We know we've got this parabola, but we got to adjust the domain. We had x being 1 over root t plus 1. Our y was the t over t plus 1, but the t had to always be greater than -1. Obviously, it's got to be greater than -1, so it's not, because the square root restriction there, right? And so let's go ahead and make a table of values here with t and x. It's got to be greater than -1, because if we shoved in -1, I'd be dividing by 0. I can't do that, so we know that's undefined, right? So this is an open point. There, go up into that. And then, we could throw in, let's put in values really close to -1, like -0.999. So we'll get right up to it real close. We throw in 0. I know that if we threw in 0, I'd have 1 over 1, right? Throw in 1, and we'll get bigger after that. And I'm just going to take my calculator, I'm going to punch it in to here. So I've got 31.6227 for that, -0.99, 10 for that. Got these values. You can see as t is greater than -1, but as let's make a note here. you know, as you see how as we get larger with our t, we're approaching 0 here. As t shoots to infinity, at least on the right hand side, as you're greater than 1, x approaches 0, right? Your domain on this is, and see how your x's here are all bigger than 0. X is greater than 0. That's your domain on here. Okay. You could also plot a few more points. All right. Remember, we know this is a parabola reflected about the x-axis and bumped up 1. We know at t being -1, we're undefined, but we could throw in a few other points. You know, like -3/4 would spit out 2, and -3 for the y. Throw in 0, we know gives that 1 for x. It'd give a 0 for y. 3 would be a good one, because I get a half here, and I get 3/4 for the y. And then of course we can graph this thing. So we got 0, 1. I'm not hitting that. I hit 2, -3. 1, 0. So maybe I should draw this a little better. One, 0, 2, -3. I got a half, up 3/4. But as t is increasing in value, right? As t goes from -3/4, it's at right here. And then when t goes to 0, it's right here. And when t is 3, it gets to the 1/2, 3/4 right there, and so on, right? And so my orientation is got to be going like that. Whoops, I didn't draw that very good, but up until then, right? And that's a pretty decent graph of that parametric equation with the adjusted curve. Let's go ahead and sketch one here as well, and t between -2 and 6. Kind of gets tedious with these. So again, we're just plugging it into x and y for those t values. And so you get 0 here. You get square root of 2 here, which is like 1.4. You get 2. You get square root of 6. You get square root of 8, almost 3, right? Get square root of 10. Square root of 12, square root of 14, square root of 16, which is 4. And then let's do for the y. If t is -2, now let's plug it into here for the y value. So -4 plus 1 get -3. 1, 1, 3. And let's go ahead and draw these. Now note also here my x is greater than or equal to 0, right? Just keeps going up. But let's go ahead and draw this. Let me do it over here. And I'll use some of these points. 0, -3. Let me use like 2, 1. That's almost 3, 5. And use those. So it's for t being -2. Square root of 8, 5, 4, 13. Anyways, we could keep going with this, but more points, but we'll go up to that terminal point there at t being 6. Now let's go ahead and eliminate the parameter. So we have x being square root of 2t plus 4, and then our y was 2t plus 1. And so let's go ahead and solve for t here. So I'm going to square both sides. I got x squared equals 2t plus 4. And let me subtract 4 on both sides. So I got 2t equals x squared minus 4. Divide everybody by 2. I got x squared minus 4 all over 2. Now I'm going to throw that in right there. So y equals 2 times x squared minus 4 all over 2 plus 1. So we got y equals x squared minus 4 plus 1. So x squared minus 3. But note our domain was only greater than or equal to 0 for the x values based on the t, right? Because our x's were greater than or equal to 0. The center of 4, right? So that's the domain of this rectangular is actually, it actually goes from 0 up to 4. So let's be more precise about my domain of this rectangular equation. So we've got x squared minus 3, but it's only between 0 and 4 is my domain. X such that. Notice I got another set of parametric equations. X equals t squared, y equals t plus 1, but t is just all real numbers. And so what we're going to do is we're just going to go ahead and pick some table of values. Let's just do it between -3 and 3, just to sketch the curve. So we'll get a feel for this. X is t squared, so we got 9, -2 squared, -1 squared, and so on. And then we got t plus 1, so I got -3 plus 1, -2, -2 plus 1, -1. And there's my points. I'm going to start with 9, -2. For t being -3, and then I'm going to go to 4, -1, then I'm going to go to 1, 0, then I'm going to go to 0, comma 1, 1, comma 2, 4, comma 3, 9, comma 4, and we can kind of draw this thing. Make sure you put the arrows on the direction of t here. And let's go ahead and eliminate the parameter so we know, tell us a little bit more about the shape. We know y equals t plus 1. That's a good one to solve for. T equals y minus 1. And then x equals t squared. So x equals y minus 1 squared. So y minus 1 squared equals x. If you remember your parabolas, let me go back to your conic. Here's your conic cheat sheet. You got y being squared, right? So you know it opens right or left. Well, if y squared equals positive 4a, it'd be this one right here, 4ax minus h, right? So it'll open to the right. Let me go back here. Open to the right with the vertex there at 0, 1, right? And that would be our parabola there. All right, let's do a little more parametric equations. We got some trig here. And so I'm going to go between 0 and 2 pi, it looks like. So t x here, let's go 0 pi 6. Let's go pi halves, 2 pi thirds, 5 pi 6. Let's go pi. And then we'll keep going after that. So let's plug it in one by one. So I got x equals 4 cosine of t. So we got 4 cosine of 0. Well, cosine of 0 is 1. So I have 4. Now let's throw in pi 6. I got 4 cosine pi 6 is 4 times root 3 over 2. And so I got 2 root 3. And we keep going with this, and I'm going to pause it and fill in all these so it doesn't take so long on the video, as well as let me go up to until 2 pi as well. All right, so I've got the table values sketched out. I'm going to go ahead and eliminate the parameter right now before I sketch this. It's kind of looks like it'll be a big giveaway here. You know, we have x equals 4 cosine t. We have y equals 4 sine t. And we know sine squared t plus cosine squared t equals 1. Well, sine of t from this one would be y over 4. That'd be y over 4. So that's got to be squared because sine is squared. Cosine of t would be x over 4. So we got y squared over 16 plus x squared over 16. Let me write it this way. X squared over 16 plus y squared over 16 equals 1. Let me multiply everybody by 16. And look at that, we got the equation of a circle. So the center of the circle would be 0, 0 with a radius of 4. R squared equals 16, so our radius here would be 4. Now let's go ahead and draw it as well as showing our orientation. I'm going to start out with at my initial point at 4, 0. Then I'll go, let me just pick these nice ones. And we'll do it in that order there. So we got 1, 2, 3, 4. That would be for t being 0. And then it goes to 0, 4 for t being pi halves. This is, oh gosh, I marked these wrong. Hold on, let me fix that. Yeah, sorry about that, you guys. This is pi thirds right here. And then this right here is pi halves. It'll be at 0, 4. And then this is the 2 pi thirds. All right. There we go. And then so that would hit there for the 2 pi halves. And then we hit the negative 4, 0 at pi. T being pi, it'll come down here. Then we'll hit the 0, negative 4. For t being 3 pi halves. And finally, it'll come up and hit at 2 pi back to 4, 0. So here's our orientation as it goes around the circle based on time t. All right, let's go ahead and eliminate. Instead of t, we got theta here, it looks like. So let's do theta, then x, then y. Let's go up until 2 pi. So I got x equals 3 cosine of 0. We know cosine of 0 is 1, so we got 3. And we got x equals 3 cosine of pi halves. I know the cosine of pi halves is 0. So we got 0 and so on. Now let's do it for the y's. 4 sine of the 0 is 0. 4 sine of pi halves. I know sine of pi halves is 1. So 4 times 1 is 4. And so on. Now we've got our points here. We can draw this. Now before I draw it, I'm going to go ahead and eliminate the parameter again. I know sine squared theta plus cosine squared theta is 1, and the sine of theta is y over 4. The cosine of theta is x over 3 from the first equation. So I got x squared over 9 plus the y squared over 16 equals 1. So this is an ellipse. If you look back at your conics cheat sheet, if you remember from your conics. This is an ellipse. A is always bigger than B, and so this thing is your major axis is vertical, right? So it's this one right here. Your A number is bigger. Your A is bigger than your B, right? So let me go back here. So right here, that's your A squared, right? And so this is an ellipse. It's centered at, let me go ahead and write it this way. Centered at HK. Alright, so it's an ellipse centered at 0, 0. We'll talk about the tracing in just a minute, but the major axis is vertical, right? So it's elongated vertically. And the vertices, that comes from the 16. A squared is 16. So the vertices, distance from 0, 0, so it'll go up 4 and down 4. And then the co-vertices would be from the B. B squared is 9. Right? So B is plus or minus, B is 3. So it'd be plus or minus 3, 0 on those co-vertices. But let's go ahead and sketch it now using our points. We got 1, 2, 3, 0. We're going to start there at T being 0. We're going to go up to 0, 4. Then we're going to go to negative 3, 0. Then we go 0, negative 4. Then we go back to 3, 0. So here's your orientation of the ellipse. So it's traced counterclockwise, right? Traced counterclockwise in this case. Is the orientation of this ellipse. Set of parametric equations that creates an ellipse. I put a little note in here. Just note that when you eliminate the parameter, it's just helping us to sketch the curve, right? But we still need the parametric equations to tell you the position, direction, and speed at any given time t, right? We need to know that orientation. And so let's go ahead and do another one here. And let's identify the curve. Let's just practice identifying, is it a line, parabola, circular ellipse, or hyperbola? Well, we know sine squared of whatever, in this case 3t, plus cosine squared of that same angle is 1, right? And we know from that the sine of 3t from this equation would be y over 2. So I got y over 2 being squared. And then from this one, I have cosine of 3t equals x over 2. So x over 2 is being squared here. So I got x squared over 4 plus y squared over 4 equals 1. I multiply everybody by 4. And it looks like we've got another circle again. Centered at 0. So we've got a circle centered at 0, 0 with a radius. R squared equals 4, so the radius is 2. Do another one here. Now notice this one, it's not like we have sines and cosines and stuff. We have x equals 2t plus 1. So I'm just going to go ahead and I'm going to take that equation and solve for t, 2t plus 1. So I'm going to subtract 1 from both sides. So I have 2t equals x minus 1. So t equals x minus 1 all over 2. And then I'm just going to substitute it in to this t squared minus 3. So I got x minus 1 over 2 being squared minus 3. So I got x minus 1 being squared over 2 squared minus 3. And if I add 3 to both sides, I got y plus 3 equals x minus 1 quantity squared over 4. Multiply this side by 4, this side by 4. Bring it up here. So I got x minus 1 quantity squared equals 4. Y plus 3. So if I look on my conic sheets, if only the x or the y is being squared, right, the x is being squared in this case. Here, let me pull up my electronics sheet. Then I know that this thing is a parabola, and the x is being squared, right? So this thing will open up or down based on if it's positive or negative. So let's go back here. So we've got a vertex at 1, and the k is -3. So this is a parabola. It opens up, right? That's a +4 there in front. Got the vertex at 1, -3. And this may be of some use. It's kind of a little cheat sheet here. Figure out, get a circle, ellipse, hyperbola, and so on. Notice t, there's no restrictions on t, so you can assume that t is all real numbers. And I'll just start it. Let's do like a -2 up to 2. And let's just plug them in one by one here. So x is 5 minus 4 times -2, so 5 plus 8, I get 13. 5 plus 4, I get 9. Now let's do the y is 2 plus 5t, so 2 minus 10, -8. So I got 13, -8, that's way out there. Let me do the 9. 9, -3, I got 5. 2, I got 1, 7, and so on. I could draw some more, but call it good there. This is for t being -1, t being 0, t being 1, and so on. And let's go ahead and eliminate the parameter and make sure this is a line. It looks like a line to me. So we get x equals 5 minus 4t, so 4t equals 5 minus x. So t equals 5 minus x all over 4. And then we got 2 plus 5t is the y. So I get 2 plus 5 times 5 minus x all over 4 when I plug that in for t. So y equals 2 plus, let me distribute that. I got 25 fourths minus 5x over 4. This is over 1. Let's get that out of the common denominator. 4, so times 4 times 4. So I got y equals -5 fourths x plus 33 fourths. So we definitely have a line here as we drew. Right here, let's go ahead and doesn't look like I have any restrictions on t. Let's do t being -2 again up to 2. So t, I got x is 1 plus 1 over -2. And a half, I got 0, and I got t, that'll be undefined here. Can't divide by 0. 1, 2, let me do one more here. 2, I got 3 halves. 4 thirds. Now let me find my y. T minus 1, -2 minus 1, -3. -1 minus 1, -2. And I could look at this. Let's see here. I got half, -3. I got 0, -2. And then I got 2, 0 over here. I got 1.5, comma 1, 3 halves, comma 1. I got 1 1/3, comma 2. So I'm kind of like, boy, what is this thing? I don't know. Let's go ahead and eliminate the parameter. Kind of help us out here. So we got x equals 1 plus 1 over t. So 1 over t equals x minus 1. So t would be 1 over x minus 1. And so y equals t minus 1. Let's plug the t in. So I got t is 1 over x minus 1 minus 1. And so this, the parent function is the rational function 1 over x. We know the rational function 1 over x from pre-calc looks like this, right? It's got a horizontal asymptote y equals 0. I'm sorry, vertical asymptote x equals 0, horizontal asymptote y equals 0. And that's kind of what it looks like. But this one will move it right 1 and down 1, right? And so if you want to put on there the vertical asymptote, then would be right 1. The horizontal asymptote would drop it down 1. That can be very helpful when you're drawing this. And we could plot some more points, but now we have an idea, and we're like, oh, that means it looks the same as that y equals 1 over x, except right 1, down 1. So the elimination of the parameter really helped us. Now t, when t is -2, it's at a half. This is for t being -2. This is for t being -1. So I want my orientation of this thing going like that, right? And then when t is 1, I'm right here. T is 1, t is 2, and so on. So I'm going this way, my orientation on that one. Okay. For this, I'm going to go ahead and actually eliminate the parameter first on this one. Notice I got x equals e to the t. Well, e to the whatever is always positive, right? If you think about e to the x, right, here's y equals e to the x. Doesn't matter what the x is, it's always positive, right? And so that's of note here. If e to the t is always positive, well, x is always going to be positive, right? Let's go ahead and take the natural log of both sides to undo e. So we got t being the natural log of x. And then let's shove it into y equals e to the 3t plus 1. Let's throw that in for t times t, the ln of x, plus 1. Now I'm going to use the power rule here. So that is e to the ln of x cubed. So e to the ln of x cubed is just x cubed. So I've got a cubic, right? I think about, here's my cubic, but I got to bump it up 1. So it's going to look like that. But remember, I had the restriction, x has got to be greater than 1. I'm sorry, x has got to be greater than 0. So if I bump the whole thing up 1, but it's got to be greater than 0, that's kind of what this thing's going to look like. But let's go ahead and plug some points in. Let's do 0. E to the 0 is 1. And then y equals e to the 3 times 0 plus 1. So 1 plus 1 is 2. Then I'm going to be strategic here and throw in like the natural log of 2. That'd be a good one. Because e to the t, e to the ln of 2 is just 2. And then y equals e to the 3 ln of 2 plus 1. That's e to the ln of 2 cubed plus 1. That's 2 cubed plus 1. That's 9. And so now we can kind of draw this thing. Because we already have a pretty good idea what this thing looks like anyways. We're not hitting there, but we do hit at 1, 2. Remember, x has got to be positive. We know that. Hit at 1, 2. That's for t being 0. And then 2, 9. Okay, kind of making a mess here. But anyways, there's the orientation of that thing. So it's a cubic. Alright, this is a good problem to another you try it problem if you want to pause the video. Let me go ahead and eliminate the parameter first. I know sine squared of 2 theta plus cosine squared 2 theta is 1. And the sine of theta is x over 6, so that would be x over 6 squared. The cosine of theta from that, cosine of 2 theta, sorry, is y over 4. That's also being squared. So I get x squared over 36 plus y squared over 16 equals 1. So I've got an ellipse. A is bigger than b, so that a squared is going to be the 36 there. So the major axis is horizontal, is centered, is 0, 0 again. So it's elongated horizontally. Major axis is horizontal. The vertices, a squared is 36. So 6 to the right, 6 to the left from the center. So plus minus 6, 0 would be my vertices. The co-vertices, which come from the b value there, be 0 plus minus 4. Let's go ahead and plot some points here. Theta, x, y. Go with 0. Sine 0, 0. We go pi 4 should be a good one because when I throw in 6 sine of 2 times pi 4, see how it gives me the pi halves. I know the sine of pi halves is 1. So I get 6. And then I'd go like pi halves. I'd go like 3 pi 4s. Pi to be another good one. 0, 4. And then another way to think about this too is your period on this is 2 pi over that 2, right? So if I split pi up into a fourths of that, so I go up pi fourths each time, up pi fourths, up pi fourths. So that'll be some real nice spots to plug in, right? That's another way to think about that if you're struggling on how to put the points in. All right, so we got 0, 4. My first one, this is when theta is equal to 0, and then it goes to 6, 0. And this is for theta being pi 4s, and then I go to 0, negative 4. Comes around here, and then negative 6. And that is like the all-time worst freaking ellipse. I can't draw these things, but anyways, my orientation of this way. Orientation's this way, so I'm a clockwise orientation here. We got another good you try problem. If you do want to pause the video, that'd be great. I'm going to go ahead and eliminate the parameter first. I know 1 plus tangent squared equals secant squared theta. And from the second equation, tangent theta would be y over 3. From the first equation, secant theta would be x over 4. And so we've got 1 plus y squared over 9 equals x squared over 16. So x squared over 16 minus y squared over 9 equals 1. Notice I got a minus here. So this is a hyperbola centered at 0, 0. Here's my a squared is 16, right? So my transverse, it's going to open right, left. So this thing's centered, I should say hyperbola, centered 0, 0. Transverse axis is horizontal. So it's going to open right and left. The vertices, which is a distance away, a squared is 16. That'll be at plus minus 4, 0. And, I can kind of draw here, let me draw. So I'm a distance away from the center. And then when we did hyperbolas, if you remember, you would go up B amount if it opens right, left, and you draw this like imaginary box here that kind of helps us see how wide the hyperbola is. So notice I'm going up a B amount. Oops, that's totally wrong. I'm supposed to be up. I'm only supposed to be up 3, you guys. Sorry about that. Of course. 1, 2, 3. Okay, there we go. And these diagonals that go through the center and the corners of this box, they kind of help me draw my hyperbola. So my hyperbola is kind of like this. I know I don't have any points yet, but that's kind of giving you a feel for that. So your asymptotes are y equals plus or minus, in this case, up b over a. So in this case, up 3 and over 4x. Like that's those diagonals. All right, let's go ahead and plot some points then. So we've got theta, we've got x, we've got y, and we have x equals 4 secant theta. We got y equals 3 tangent theta. Let's go 0. So pi force be a good one for that tangent. Secant. Pi halves. Let's get a few of these points. How about 3 pi force and then pi. Let's throw those in one by one. So I got 4. I got 4 times the secant of pi force. That's 1 over cosine pi force. So I got 4 over root 2 over 2. So that's 8 over root 2, or 8 root 2 over 2, or 4 root 2. So we got 4 root 2, which is about 5.657. Okay. Pi halves, that would be undefined right here. This would give us negative 4 root 2, and that would give us negative 4. Now let's do 3 tangent of theta. So we got 3, we got sine of 0 over cosine of 0, so we got 0. And then we're plugging in the pi force. Now we got 3 sine pi force over cosine pi force. Of course, those are the same thing. So we got 3. Pi halves, that'll be undefined. 3 and 0. Alright, so we got 4, 0, and then 5.657, 3. So I'm starting here. This is for theta being 3. I'm sorry, theta being 0. I have 4, 0. When theta is pi force, I got 5.6, 3. So about right there. That's for theta being pi force. It's undefined for pi halves. 3 pi force jumps over here. Negative 5.567, negative 3. That's for theta being 3 pi force. And then it hits right here for theta being pi. So my orientation is like that for my hyperbola. All right, now what about if we go in reverse? How can we determine a set of parametric equations for a given graph or a given physical description, right? So let's come up with that. So let's find 2 different sets of parametric equations for the graph of this parabola, y equals 1 minus x squared. And we'll do it 2 ways. So let's do solution 1. We'll make it real easy, and we'll just pick x being t. Well, if that's true, we know x is t, then y would be 1 minus t squared. And so my parametric equations is x is t and y is 1 minus t squared. So that's probably the easiest one to do first. But it says do it at least twice. Let's just pick the next one. How about 2t minus 1? Well, we have y equals 1 minus x squared. So that'd be y equals 1 minus 2t minus 1 squared. So y equals 1 minus, that'd be 2t minus 1, 2t minus 1. So we got 1 minus 4t squared minus 2t minus 2t is minus 4t plus 1. And I got to distribute that. So we got y, and notice the 1 minus 1, that's gone. We got negative 4t squared plus 4t. So x we picked to be 2t minus 1, and our y is negative 4t squared plus 4t. And both of these represent that parabola. And both sets of parametric equations represent y equals 1 minus x squared, that rectangular equation. Well, I hope that kind of gets you started on parametric equations and curves and parameterizing and all that. Thanks for watching. Taking notes. See you next time.